I want to talk about what I think is an interesting problem in numerical linear algebra, namely Crouzeix conjecture. I'll talk about how we can study this numerically, and then talk about, well, what if we look at large random matrices? Does Crouzeix conjecture hold? What can we say about it in that case? So we've heard a lot about eigenvalues, and eigenvalues are great and all that. Let A be an n by n matrix if A is diagonalizable and F is any analytic function, analytic in a neighborhood of the spectrum of A. Then, of course, the spectral mapping theorem, F of A is D times F of lambda times B inverse. And if you're interested in the norm of F of A, which we frequently are, one can say that's less than or equal to the norm V times norm V inverse, or the condition number of V, times the maximum value of F on the spectrum, okay? And here in this talk, I will always be talking about the two norm or the spectral norm for matrices. And as long as the condition number of an eigenvector matrix, say the best conditioned eigenvector matrix, is of moderate size, then the eigenvalues tell us pretty much what we need to know about norm F of A. However, this is not always the case. We're often interested in powers of a matrix A, for example, and the powers of A go to 0 as K goes to infinity, if and only if the spectral radius of A, the maximum absolute value of an eigenvalue of A, is less than 1. And moreover, for K sufficiently large, this spectral radius tells us about the rate at which the norms of the powers of A go to 0. But it doesn't tell us what happens if K is not sufficiently large. You can take two matrices with exactly the same eigenvalues. This one is a normal matrix. It has a complete set of orthonormal eigenvectors. And the norms of the powers of this matrix go to 0 monotonically. This one has rather ill-conditioned eigenvectors, and it grows first by 10 orders of magnitude, does some funny stuff, and eventually will go to 0 at the same rate as this one. But we're often interested in what happens before you reach that asymptotic regime. Similarly, if you're solving differential equations, y prime equals ay, the solution is y of t equals e to the ta times y0. And once again, eigenvalues tell us what happens asymptotically as t goes to infinity. If the eigenvalues are all in the left half plane, then asymptotically norm e to the ta will go to 0. However, again, things can happen before we reach that asymptotic region. Again, two matrices with exactly the same eigenvalues, all in the left half plane. This one has perfectly conditioned eigenvectors. It's a normal matrix, and it goes to 0. The e to the ta goes to 0 monotonically with t, while this one has very ill-conditioned eigenvectors, and it does strange things, growing by about 5 orders of magnitude before eventually going to 0 at the same rate. We've heard a couple of talks about GMRes. The GMRes algorithm for solving AX equal B constructs an approximate solution from a Krylov space, so that the norm of the residual at step K is the min over all kth degree polynomials with value 1 at the origin of the norm of P of A times the initial residual, okay? So one might think, well, okay, if I can make such a polynomial small at the eigenvalues of A, then GMRes will converge well. For instance, if the eigenvalues are all clustered around 1, say, you can take a polynomial with value 1 at the origin and make it very small at all those eigenvalues. However, that's not sufficient for good GM-res convergence. In fact, one can show that any non-increasing convergence curve is possible for a matrix having any given eigenvalues. And a simple way to see that eigenvalues alone won't do the trick is to look at a matrix with this sparsity pattern. You can construct such a matrix with this sparsity pattern that has any eigenvalues you want. For example, you could take a companion matrix with ones here and the coefficients of the polynomial you want down here. What happens if your initial residual is the first unit vector? Well, what GM-res will do is it will take that initial residual, orthogonalize it against A times the first unit vector. That would be some multiple of the nth unit vector. It's already orthogonal, so it makes no progress. The next step, it orthogonalizes against A times the first unit vector, plus A squared, and A squared times the first unit vector. So that's going to be some linear combination of the nth and n minus first unit vectors. The initial residual is already orthogonal to that. It makes no progress. Next step, it's going to be orthogonalizing against Cn minus 1, and Cn minus 2. And again, no progress until step n, where it gets the exact solution. So eigenvalues alone do not tell you anything good about GM-res convergence unless you also have some information about the conditioning of the eigenvectors. All right, so for these reasons, people look at other things besides eigenvalues. And one thing that people look at to try and better describe the behavior of the norms of functions of the matrix is the field of values or numerical range. This is the set of values, the inner product of AQ with Q, such that norm Q is 1. This is a compact convex set. That's the Toeplitz-Hausdorff theorem. It contains the spectrum, but it may contain much more. Here are some examples of fields of values. I made them all look like disks. They don't have to look like a disk. They can be elliptical. They can be any sort of convex shape. They can't be too weird. For a normal matrix, the condition number of the eigenvectors is 1. The numerical range or field of values is just the convex hull of the eigenvalues. Roughly, as the eigenvector matrix becomes more conditioned, more ill-conditioned, this is just roughly, the field of values looks more larger than the eigenvalues themselves. It contains a lot more area. Okay, this is a matrix whose eigenvectors have condition number about 22. When we go to 227, now the eigenvalues are here, and this was its field of values. And when we go up to a matrix with condition number 1.8 e plus 3, now the eigenvalues on the graph with the field of values look sort of like a dot. So the field of values gets larger roughly as the eigenvector matrix becomes more ill-conditioned. All right, so what is Crouzeix' conjecture? In 2004, Crouzeix conjectured that the field of values is a two-spectral set for A. That is, for any function f analytic in W of A and continuous on the boundary, the norm of f of A is less than or equal to twice the maximum value of f on the field of values. Okay. Now, note that 2 is best possible. Here's a matrix. Its norm is 2. It's 2 norm. Its spectral norm is 2. It's not hard to see that its numerical range is the unit disk. So if you just take f of z equal to z, then norm f of A is indeed equal to twice the maximum value of f of z on the numerical range. In fact, the only way that one can get 2 with a monomial, okay, with just a simple power of z, is basically if the matrix A has this form. Now, this matrix has been rediscovered several times recently. The earliest place I could find it was in a paper from 1971 by Crabb. So we call it the Crabb Matrix. And it's just a Jordan block, but with root 2 at either end. Okay. So the only way that one can actually achieve this upper bound of 2 with a monomial is if the matrix is essentially this one. That is, it should be unitarily similar to this matrix, and it could have another block. It could be a direct sum of this matrix and another block whose numerical radius is whose numerical range is inside the numerical range of this one, because that then would have basically no effect. So the numerical range of this matrix, one can show, is the unit disk. When you raise this matrix to the n minus first power, everything becomes 0 except in the upper left corner where it becomes 2. So the norm of a to the n minus 1 is 2, but the maximum value of z to the n minus 1 on the unit disk is, of course, 1. So we get that ratio of 2. Feel free to interrupt with questions at any time. Are there questions so far? All right. Well, we know some things. What are some known results? Well, obviously, if A is diagonalizable and it has an eigenvector matrix with condition number less than or equal to 2, then Crouzeix conjecture holds for that matrix. Norm f of A is less than or equal to twice the maximum value of f on the spectrum. So it's certainly less than or equal to twice the maximum value of f on the numerical range. In 1975, Okubo and Ando showed that if D is any disk containing the numerical range, then D is a 2-spectral set for A. Norm f of A is less than or equal to twice the maximum value of f on the disk. So, of course, if the field of values itself is a disk, then Crouzeix conjecture holds. In 2007, Crouzeix was able to show that the numerical range is an 11.08 spectral set for A. The proof was very complicated, and he said, in order to improve it drastically, it is clear that we have to find a completely different method of proof. Well, what? All functions that are analytic within the field of values and continuous on the boundary. Yeah. Yep. Well, there was a breakthrough in 2017. The conjecture wasn't proved, but people came awfully close. Crouzeix-Palencia showed that the numerical range is a 1 plus the square root of 2 spectral set, a 2.415 spectral set. The conjecture constant 2 remains open. And I highly recommend this paper. It's 6 pages long. It's very short and a little dense, but it's a pretty elementary proof, most parts of it. Let me just give a sketch of the proof. It's a little bit different from the one in the paper. I think it's maybe a little more revealing and maybe even simpler in some ways than the one in the paper. Suppose we have the function f hat, and at least for matrices, there is a function f hat that achieves the maximum of the Crouzeix ratio. So suppose f hat maximizes the Crouzeix ratio over all functions. We'll take it to have infinity norm 1 on the numerical range. We can normalize it so that then I don't have to divide by its infinity norm. Let u1 and v1 be the left and right singular vectors of f hat of a corresponding to the largest singular value, sigma 1. Well, one can easily show that if you take any function h with maximum, with infinity norm at most 1 on the numerical range, and you apply it to u1, or you apply h of a star to v1, or you look at u1 star h of a star v1, you get these inequalities. And I won't write down all of the proofs, but they're one-liners. They simply follow from the fact that f hat is optimal, that no other function with infinity norm 1 on w of a can magnify v1 more than f hat of a does. So for instance, to get this, note that h of a, f hat of a times d1, well, f hat of a times d1 is just sigma 1 times u1. So if this is going to have norm less than or equal to sigma 1, the norm of f hat of a times d1, then norm h of a u1 has to be less than or equal to 1. Okay? So the others follow similarly with a one-line proof. All right, so with that in mind, suppose there is a function h with infinity norm at most 1 on w of a that also satisfies u1 star f hat of a plus h of a star times v1 in an absolute value is less than or equal to 2. Then you get the Crouzeix-Palencia result because you just get a quadratic equation to solve. u1 star f hat of a times v1, that's just the norm of f hat of a, or sigma 1. We said the absolute value of u1 star h of a star v1 must be less than or equal to 1 over sigma 1. So we'll get the least restrictions on sigma 1 if it turns out that this is actually equal to negative 1 over sigma 1. And then all this tells us about sigma 1 is that sigma 1 minus 1 over sigma 1 is less than or equal to 2. So we just solve the quadratic equation and get the result. So, very simple proof. Now, a slightly harder part is showing that such a function h exists. Crouzeix and Palencia showed that if you define h of a to be the Cauchy transform of the complex conjugate of f, then it satisfies the hypotheses of the theorem. Note that since the complex conjugate is not an analytic function, this is not like the Cauchy integral formula. If I had f here, this would just be equal to f of a. But since it's the complex conjugate of f, which is not analytic, it's less clear what this is equal to. But they showed that it satisfies the hypothesis of this theorem, and therefore we're done. So it's a very simple proof idea. Okay, so being unable to prove the result, we decided to do some numerical experiments. Michael Overton and I used a BFGS code method to try to minimize, well, we called this the Crouzeix ratio, though I usually think of the Crouzeix ratio as being the inverse of this. But the maximum value of P on the numerical range over norm P of A, where P is a polynomial of some fixed degree. So we can fix A and minimize over P, can fix P and minimize over A of a given dimension, or we can minimize over both P and A. We didn't find any counterexamples. The ratio always came out to be greater than or equal to a half. Now, one interesting thing that we thought we found was that when we used 100 initial guesses for A, and for the coefficients of P, we took P to be of degree at most n-1, we set them randomly using the standard normal distribution. The code almost always converged either to a half, which we believe is the globally optimal value, or to 1, which is locally optimal. Okay. And so we thought at the time, well, maybe those are the only two, local mins. However, Michael was giving a talk about this, and I think Martin Heyer suggested that he try a different kind of distribution for the initial guesses. So he tried an exponential distribution, taking the guesses to be of the form x times e to the alpha x squared, where x is from the standard normal distribution, and alpha was 2. And with that initialization, he actually found many local minima. Here I've just taken some examples from the paper. Got a local minimum when the ratio was a half, got a local minimum when the ratio was 1, but also found some local minima for a number of different ratios. All right, but I find it hard to interpret these results because we're limiting the degree of the polynomial, and we really don't have to. Another way, in some ways a better way, I'd say, to study this problem is the following. We actually know the form of the function that all right, I'm now going to take the inverse of what Michael is minimizing. We know the form of the function that maximizes the Crouzeix ratio, norm f of A over the maximum value of f on the field of values. It's of the form decomposed with phi, where phi is any conformal mapping from W of A to the unit disk, and B is a Blaschke product, a degree at most n-1. What is a Blaschke product? Well, it's something of this form where the alpha j's in absolute value are less than or equal to 1. Often it's written with the alpha j's strictly less than 1. But if you plug in an alpha j with magnitude 1, this is just a unit scalar, so it doesn't matter. B maps the unit disk to itself and the unit circle to itself. And I think Blaschke products are not used in the numerical analysis community as much as they should be. They solve a nice optimization problem. Why is the optimal function of the form decomposed with phi? Well, f of A is completely determined by the values of f, and perhaps some of its derivatives, if A is not diagonalizable, at the eigenvalues of A. Of all functions analytic in the disk and taking given values at n given points, the one with smallest infinity norm on the disk is a scalar multiple of a Blaschke product of degree at most n-1. All right, so what numerical method do we use? We use Cheb-Fun to compute the numerical range and a conformal mapping phi from W of A to the unit disk. Use an optimization code. I just used fmin-con. There are probably better ones, but that's the one in MATLAB, and it works pretty well on these problems, to find the roots of the extremal Blaschke product, find the roots that maximize norm B of phi of A. We don't have to divide by its infinity norm on W of A because that's 1. Now, All right, so we run this code, we get a result. Do we have any faith in the result? Well, a certain amount. Several things are known about the optimal Blaschka product, V hat. The simplest was actually shown by Crouzeix-Palencia and Holbrook in 2014. If you write the singular value decomposition of V hat of phi of A as U sigma V star, then the left and right singular vectors corresponding to the largest singular value are orthogonal to each other. So we can check that. In a paper with Bickel, Gorkin, myself, Ransford, Schweninger, and Begert, 6 people, we derived a number of other properties of this extremal Blaschka product. For example, if you can factor it in the form F1 times F2, then this relation has to hold. So, and there are a number of other properties that have to hold. Even with all of these properties, these are necessary conditions for the extremal Blaschka product, V hat, but not sufficient. However, we can check at least that those conditions hold. We're never completely sure that we have the true global optimal, but using many different initial guesses for the roots of the Blaschka product, we think we're finding the global optimal. In special cases where the optimal V hat is actually known, we get it right. So some faith in the numerical results. Now, we've done lots of experiments with small matrices. And one of the things we found, and we don't really fully know how to explain this, is that the degree of the optimal Blaschka product, while it could be as much as n-1, it's often a lot less than that. For 3x3 matrices, okay, fine, it's 2 most of the time. 4x4 matrices, it's 3 occasionally. 5x5 matrices, I think I tried 500 of these and maybe one of them had a degree 4 Blaschka product. Usually the degree is low. Okay, questions on anything so far? Yeah. All right, that's the next slide. Yeah, so I think Tyler Chen and Tom Trogdon asked me, could I do the experiment on large random matrices? And my first reaction was no. With 100 by 100 matrix, I don't trust the optimization code to find 99 optimal roots of a Blaschka product. But then I thought, well, let's just try it. Let's limit the number of roots I allow it to find. Let it find, say, 8 optimal roots of a Blaschka product. And what I found was that it actually came back with 7 of the alpha J's having absolute value 1, meaning that they don't contribute to it. And the Blaschka product actually had only 1 root. This was for a 500 by 500 Geneva matrix. It's known that the eigenvalues, when you scale it by root 2, 1 over root 2n, fill the unit disk. The numerical range approaches a disk of radius square root of 2. And well, we found the optimal V hat. Now, by symmetry, I would have thought that V hat of Z would just be equal to Z, okay? But of course, since it's a finite matrix, it's not perfectly, the eigenvalues aren't perfectly symmetrically distributed. So we found a B hat that made such that norm B hat of phi of Z was actually a little bit larger than norm phi of Z, but not much, and it was of degree 1. And even though I allowed it to, now it could be that if I had allowed it to have degree 9, I would have gotten something different, but I'd be surprised. Okay. So as I said, the field of values well, not only appears to approach a disk of radius 2, but has been shown to approach a disk of radius root 2. With 10 test matrices of size n equal 500, norm b hat of phi of a ranged from 1.4198 to 1.4336. So we think that in the limit, norm b hat of phi of a will converge to root 2. That is, that for a large Geneva matrix, the numerical range is actually a root 2 spectral set. And similar results were obtained with other distributions. That is, W of A approached a disk. The optimal B hat appeared to have degree 1. Norm B hat of phi of A appeared to approach the square root of 2. I tried real matrix entries, normally distributed, real or complex matrix entries from a uniform distribution, tried a banded matrix where I took n equal to 500 and took the half bandwidth to be 50, again with real and imaginary parts from a standard normal distribution. And for all of those matrices, the results look very similar. So not only does Crouzeix' conjecture hold, but we actually get a better estimate. The numerical radius is a root 2 spectral set. Now, since this exponential sort of distribution led to different results in our optimization code, I thought, well, let's try that. And it led to different results here as well. Okay. The extremal Blaschke product, again, had degree 1. In fact, to as many decimal places as I printed out, B hat of Z was actually equal to Z. That was the optimal Blaschke product. Here, the ratio is very close to 2. Okay? So this one actually matches the Crouzeix bound. Now, I said earlier, the only way you could match that bound with the monomial, and in this case, the monomial is just Z. The only way you could match that bound with the monomial was if the matrix is unitarily similar to a 2x2 Crabb matrix, or 0, 2, 0, 0, followed by another block whose numerical range is inside that of the first block. It's not at all obvious to me that the matrix we got out that the matrix any of the matrices here were of that form, but of course they wouldn't be exactly of that form. They may be close to of that form, but I can't really verify that. These matrices had, if you normalize them so that the numerical radius was 1, the numerical range was the unit disk. On this graph, the eigenvalues just look like a dot. They're the eigenvectors are extremely ill-conditioned. If you plot the eigenvalues on a graph with axis 10 to the minus 9, then you see some structure. But these matrices come close to achieving that worst case 2, what we believe is the worst case. Someone in an earlier talk mentioned the following type of matrix. Take a matrix X with real normally distributed entries, do its QR decomposition, and then take a block, an upper left block of the Q matrix. Of course, if we took the whole Q, that would be a unitary matrix. Its eigenvalues would all be on the unit circle. When we do that, the eigenvalues now tend more towards the unit circle, towards the boundary of the field of values. Okay. And in this case, the optimal B hat seemed to well, it had higher degree. We definitely found B hats of degree 4 and even higher that were better than taking a p hat of degree 1. Okay. And well, I since I didn't allow the full degree, which would be 399, I don't know that my results from the optimization code really tell us exactly what b hat is in this case. So this is a different kind of case, a more complicated one as far as the optimal Blaschke product. Okay, so let me just say conclusions and maybe some guesses. It was always thought that if there was a counterexample to Crouzeix' conjecture, it would be revealed with a small matrix. Well, none of this work contradicts that. I think I believe that even more. Large matrices are too regular in some sense. I guess this has actually been proved that for large classes of random matrices, W of A, the numerical range, approaches a disk as the matrix size goes to infinity. So Crouzeix' conjecture is known to hold that if W of A is a disk. For Geneva matrices and matrices from similar distributions, it appears that the Crouzeix ratio converges to the square root of 2 as the matrix size goes to infinity. All right, I think that's what I had to say. I just want to say thanks to Tom for organizing and to all the participants, especially those who stayed through the last day.